Hi, Gen Chem 1 lab students. This is your pre-lab video for week 2 of Gen Chem 1 lab. This week's exercise is going to be uh, building on what we learned last week. So last week we did the experiment demonstrations to learn how to make observations. And then we did experiment 1, understanding significant figures. You may want to reread through that introduction again because the same principles are going to apply today. You also, of course, need to complete the lab report, which is to complete pages 20 through 25. And you're going to just answer all those questions, do all of that math. And when you get to lab this week, you'll staple that together and turn it in at the beginning of lab. Reports are accepted late, but I don't recommend doing that unless you have difficult situations happening. But in general, it's a good idea to keep up because we're going to build on the skills we learn each week in the following experiment. So to that end, what we're going to do this week is called Experiment 2, Trace Contamination and Exploring Matter. This comes in 2 parts, so I'm going to talk about it in 2 separate pieces. But you've got to complete all the work in lab during week 2. So you're going to want to manage your time carefully and work with your partner to be strategic. So part A is called trace contamination. Okay, really, this whole experiment is about learning to identify the types of error that can happen in any scientific experiment. And so it's really important, kind of related to our conversation about failure in class. It's important to understand that error is something you cannot avoid when you're doing science, okay? Every single experiment, no matter how carefully done or how precise or how accurate, has error in it. These are things that are inherent to the universe sometimes, such as uncertainty. And they're things that are difficult or impossible to completely control. Okay. So when we're doing science, it's important to identify the types of error that we might experience. Some of you already noticed one last week. So when we were using the metric rulers, or the American rulers, actually, every single time we take a measurement, we always estimate in between the markings. That's because of a type of error called uncertainty. Okay. Uncertainty is in every single measurement. That's why I always say we can't ever take an exact measurement of something. Okay. Measurement, by the nature of the universe, is always an estimate. Okay. I recommend reading in chapter 1 about precision and accuracy. Those are concepts related to this experiment. The sections most important are 1.7 and 1.9 of your textbook, okay? Those are going to give you a foundation of what to expect for kind of your experiment this time, but also every single time we write a conclusion in science, we need to be learning how to identify error, okay? Precision and uncertainty can have different types of error. So precision means the sort of, well, remember when we were doing experiment 1 and you had the uncalibrated meter stick? That was not a precise measuring device. There were no lines on there to tell you anything between 0 and 1 meter. All we knew is that the glass was bigger than 0 and less than 1. And so the digit we recorded is an estimate, and that is the proper way to do it, 1 estimated digit. Then when we turned to the decimeter stick, there were 10 markings to show what 1/10 of a meter looked like. That was a little more precise, right? Because we could estimate 1 more figure. And then we go to the centimeter markings. Now we can estimate 3 decimal places. And then when we go to the millimeter marking, we could estimate, well, actually, that's incorrect, actually. we are measuring directly three numbers because we have lines for them. And then on the millimeter stick, we're estimating the fourth digit. That means we have more significant figures. More lines means more significant figures, which means more precision. The same principle applies when we're using something like a graduated cylinder, which is kind of like a ruler or a meter stick because it has markings on it to represent units or fractions of that unit, such as milliliters. Okay, so when we're reading a graduated cylinder, we're going to figure out the value of each of the marks and then estimate one more place value. Okay. So in our laboratory experiment, we're going to use 100 mil graduated cylinders. But first, I want to share a picture of what, like a cartoon drawing of what we're looking for here. Okay. So this particular cylinder is a 25 milliliter cylinder. So the maximum volume we are going to get out of this is 25. And then the next numbered value, the large lines go all the way around the graduated cylinder. That value is 20. So that means this is a gap of 5 milliliters. Okay. Now, I have 4 individual small graduations in between. So that means each of these must be worth 1 milliliter. So if this is 20, then 21 is right there, 22, 23, 24, and then we have 25. That means that this device has precision of plus or minus 1 milliliter marked on it. Okay. I'm going to record values from this to 1 decimal place, if that's the case. So we have markings at the 1 milliliter. I'll record my estimate at the 10th of a milliliter. This is fairly similar to the cylinder part of our experiment last week. We have an initial volume here on the left. And so I can see that the water line is a straight line. In our actual experience, it's going to form a meniscus because the water is attracted to the glass. So a meniscus looks something more like that, maybe not quite that extreme, but it looks kind of like a U shape or a circular kind of shape at the top of that. We always, always, always want to make sure we're measuring at the very bottom of that meniscus. So in this particular case, that would be right there. So just look for that when you're in the lab. You're going to always see that sort of reflection, and you want to go to the bottom of that U shape when you're measuring. Okay. You also need to be eye level. If we're not eye level, we'll be experiencing something called parallax error. That's when you're not looking directly straight at something and you're trying to measure it. My favorite example of parallax error is I was in the passenger side of one of our family cars, and my husband was driving. And I felt like he was speeding because when I looked over at the speedometer, it was around 65 and a 55. So I complained and I asked him to slow down. And he did, but he argued that he wasn't speeding very much because from his perspective, sitting in the driver's seat, so looking straight at the speedometer, he was only going 60. And apparently the message I missed is if you're going within 5 miles of the speed limit, it doesn't count as speeding. But at any rate, he has a better argument than I do because he is sitting straight, looking directly at the speedometer. Fun fact, speedometers are calibrated for people who are 6 feet tall. So if you're taller or shorter than that, there's a slight variance in the value that you're reading on a analog speedometer. But either way, it's pretty close anyway. So being eye level to the thing is really critical in getting a good measurement for everything. So we're going to kind of have to, do some squats or crouch down in order to see eye level with these things because they also need to be sitting on the counter. Otherwise, it's really, really hard to read them when they're moving around. So what we're going to make sure of is that when we look at a scaled device like a graduated cylinder, these longer lines, like this one right here, wrap all the way around the cylinder. If you're looking at it at eye level, it'll look like a line instead of a circle. So that's how we can avoid parallax error, is being eye level to whatever I'm measuring. So in this situation here, we have a reading initially where it's just past the 17. So I'm pretty certain of the 1 and the 7 because there's markings for 17. So I know where those are. We call them certain digits. I need to have one estimate in my reading of every scale device. So in this case, I'm going to estimate how far above 17 the meniscus is. Okay, and so I think it is not halfway, so I would not put 17.5, but it's a bit of a guess here because it's an estimate, and each of us are going to probably estimate this a little bit differently. I'm going to say 17.2 milliliters. So we have the right number of digits because I go one place value past the mark, and I have a unit. Both of those components are critical. So that's my initial volume here in this experiment. And then we put in a chunk of, it looks like gold maybe, and we're going to read the volume here. So for this one, our final volume, oh, they say 17.1, 17.2. These are the same reading, all right? So because our markings are plus or minus 1 milliliter, means the gap is 1 milliliter. Our precision is plus or minus 0.1 milliliters. So some of us might say 17.1, some might say 17.2, and some might even think 17.3. This is the middle of that range, so down by 0.1 milliliters or up by 0.1 milliliters is within the expected precision of this particular device. So it's based on the markings, okay? So when we're talking about precision, we're talking about what markings the device has, which is reflected in the number of digits, the significant digits, okay? Those are all about precision. Okay, anyway, so the final reading here, 19 is right there. It's above that by quite a bit, but not up to 20, just not precisely at 20. My estimate of that value would probably be about 19.9 milliliters. Theirs is 19.8 milliliters. It's okay if they aren't identical. So you and your partner should each measure these things and then compare notes. And if you're within plus or minus 0.1 milliliter of each other, that's the same measurement. Don't worry about it. That's the precision that we have. This concept here, where everybody has an estimated value for every measurement ever made, is called uncertainty. And you can't avoid it in any type of experiment. Even if robots do the measurements, even if lasers are used, there is always uncertainty. It's just a facet of the universe. We'll learn in chapter 3 why that, well, we'll learn more about uncertainty in chapter 3. I don't know that anybody really knows why it exists. Okay. Now, when we're trying to figure out the density of something, so for example, the density of your metal cylinders, density is always mass over volume. And I need to know the volume of the object I'm measuring, not the volume of the water and the object. So we'll always be doing this equation where it's the change in whatever I'm interested in this case, the change in volume, delta is the triangle here. It represents change, is equal to the final reading minus the initial reading. Okay, so in the case of this situation, the change in volume was due to putting the gold into the water. And so we'll do the final reading minus the initial. And that gives us the volume of just the gold that was put in there. That's the volume I'm going to use as my denominator. We weigh the object in order to figure out the mass of it. Oh, and by the way, 2.7 milliliters. Oh, that's supposed to be milliliters right there. Is the answer to the volume change. So in other words, the volume went up by 2.7 milliliters by adding that piece of gold in there. So if I wanted to calculate the density, I would take 51.842 grams divided by 2.7 milliliters here. Okay. That's how you're going to do your calculation from week 1 in your lab procedure. You want to make sure to review the significant figure rules in chapter 1 if those are new to you. But for this example, 2 grams in the numerator, and the denominator is 2.7 milliliters. By the way, when we're subtracting and adding, the place value needs to be what dictates your significant figures. Both of our readings go to a 10th place, so I'm making sure that my answer also goes to a 10th place. When we're dividing, it's going to be mass divided by volume, and the the significant figures is dictated by whichever one has the lowest number of figures. So in this case, 2.7 milliliters has 2 significant figures, just 2 digits, while the 51.842 is 5 significant figures. I only get to keep 2 in my answer, not 5. The calculator tells me 19.2007. That calculators don't do significant figures, so I have to keep that in mind. That's my job. And the unit there would be grams per milliliter because that's a density. So if we're only keeping 2 figures in our final answer, I'm going to round to that ones place there, which is 19. And that's our answer. Okay, that's how you calculate a density. It's also how essentially we're going to continue using those significant figure rules throughout the entire semester, and in fact, through most of your science career. So we want to be paying attention as we're working through each math problem to the significant digits. The calculator doesn't do it for us, so we're learning how to do that. I'm subtracting that initial reading of the water. That means that having different amounts of water from different people doing the experiment is not a source of error. So we would not say that anything about the graduated cylinder itself or the amount of water that we started with is error because we're subtracting that out of what we're thinking about. So the error in this experiment, in this portion of the experiment where we're filling up a volume in a graduated cylinder is just due to uncertainty. It's because every single time we take any measurement, one value will be an estimate. Every device, even if I use the same graduated cylinder and measured the same volume again as carefully as I can, the amount of material in the 2 measurements is going to be slightly different. So that's part of what we're quantifying in part A of the experiment in experiment 2. Okay, we're going to learn how different are measurements with 2 graduated cylinders. That means we could write a hypothesis about that. Okay, so as an example, a hypothesis has to be tested in the experiment, and it has to be something that you can prove right or wrong. And bonus points, I mean, not literally, but it's always great if you can make your hypothesis something numerical because it's easy to tell if you have supported that hypothesis or if you have proven it wrong. So, a potential hypothesis for the graduated cylinder comparison might be something like it is hypothesized that two graduated cylinders will have slightly different amounts of material in them when we measure 100.0 milliliters. That's a decent hypothesis. You could improve it, though. You could have some kind of guess for what you think the difference would be. So instead of saying slightly different, maybe you would say a mass difference of 1 gram or less. Okay. Your hypothesis does not need to be right to write a good lab report. In fact, I think it's easier to write a hypothesis where it gets proven wrong because when you get your conclusion, it's so much easier to think about why it was wrong and what you would do next to see what is correct. All right, so after we have measured our 100.0 milliliters of, in this case, iron 3 chloride, we're going to use a dropper to be very careful to try to get the meniscus right to the 100.0 mark. We're going to weigh before and after so that we can calculate the mass of iron chloride actually in each container. Then we're going to do some math after lab to determine the uncertainty between them. Okay, that's one hypothesis, as we talked about. The next thing we're going to do is take those two full graduated cylinders and transfer them. So I'm going to sketch out for you what's going on. I am not an artist, but that's okay. That's my graduated cylinder. Okay, and so we're going to fill them up with iron 3 chloride, which is kind of this orange stuff. And I'm going to do that twice. Okay. We weigh them before we put anything in there when they're clean and dry, and then we will weigh them after. So we could later after lab subtract those and figure out how much iron chloride is in there. Then what we're going to do is have 8 cleaned beakers. These are going to be cleaned by you guys, you and your lab partner. So each of you would clean 4 of them using soap, which in lab is just called Alkanox. They're going to be on your chemical tray, but it's also going to be in the gallon jugs that are all around the room. Okay, so the 2 pieces of glassware here are graduated cylinders and beakers. And you can also see better renditions of what these look like. There's images in the lab manual from your check-in sheet, which might be in your drawer. So you can also look at the digital version. All right, so we fill up our graduated cylinders, we do those mass weighs, we record them in our data tables in our lab notebook, and nowhere else, just the lab notebook. Then we will take our clean labeled beakers, and by the way, with labels, we want to put you and your partner's initials when we put them in the oven so that nobody steals them. And you can use a Sharpie or a wax pencil. Those are both located, well, wax one, not a regular pencil. Those are both located by my desk in the front of the room. Anyway, so what we're going to do here is take our iron 3 chloride and move it from each cylinder into beaker 1. That counts as one transfer. So if we think about this from the perspective of individual particles, like an atom, each atom moves 1 time. So that counts as one transfer from cylinders to beaker 1. Then from beaker 1 to beaker 2, we're going to do another transfer. So that's 2. And we're going to keep doing that. And we're trying with each of these transfers to make sure that we get every single drop. But of course, we all know, anybody who's ever tried to bake cookies and used a bowl too small, whenever we got to move to another container, you're going to lose some of that. You're not going to make as many cookies as you would have if you had a big enough container in the first place. And so this principle here is we're going to transfer from each graduated cylinder to beaker 1, and then beaker 1 to 2, 2 to 3, 3 to 4, and so on, in order to determine how much material gets lost when we transfer from one piece of glassware to another. This is another kind of error, so we could write a second hypothesis about it. An easy kind of way to do that is pick a mass of iron 3 chloride that you think is reasonable to lose and just write a sentence like, it is hypothesized that, I don't know, 0.5 grams will be lost per transfer between different glassware. Okay, that would be an easily testable hypothesis here. So we're going to weigh the empty cylinders and the full cylinders. And then we'll have beaker 8 empty and beaker 8 full. So by full in the context of beaker 8, what I mean is after we get to the end here and we've transferred iron chloride through all the other beakers, we're going to need to know the mass of beaker 8 so we can weigh how much iron 3 chloride makes it all the way through the process. That is going to allow us to do some subtraction and figure out initially how much iron 3 chloride did we have total in both cylinders, and finally, how much do we end with? The difference between those is going to be the amount we lose. If I take the amount we lose and divide it by 8, that will give me transfer loss per transfer. Okay, this is something we can refer to in every experiment where we have transferred material, which is going to be most of them. You'll have a quantity that you can refer back to from this experiment. Okay, so that is the transfer loss portion of part A. Once we're done with that, we're going to move on to a cleaning experiment. So I don't know about you guys, but there's this constant debate in my house about the quote unquote right way to wash the dishes. Okay. Some of us think that we don't need to pre-wash them before they go into the dishwasher. Some people rinse them before they go in the dishwasher, and some people straight up wash with soap before they put them in the dishwasher. So it's a highly variable situation in my household. In the lab, it is important to identify the best way to clean your materials so you know you're avoiding contamination. Okay, that's the trace contamination part of the experiment. Trace means a small amount. And again, this is still just in part A. We have a lot of hypotheses in this experiment. So far, we have an uncertainty hypothesis. We have a transfer loss hypothesis, and now we're talking about a sort of cleaning hypothesis, okay? So we'll have our 8 beakers from the last experiment that all have a small amount of material in them. Beaker 8 has a lot of material in it. That one we're not going to add anything to because this goes into a recycling container that we have labeled, I think, brown stuff or maybe orange stuff. It's kind of hard. The color is brown or orange depending on how, how thick the glassware is. We're going to recycle that. So we're not going to put anything into that container number 8 other than the iron chloride, and then that's going to get dumped into the bottle that's marked brown stuff. The rest of these are going to be 1 through 7 are going to be used for experiment purposes. And what we're going to do is we're going to drip in some indicator that reacts with iron. Okay, so what we're going to find in beaker number 1, this is going to be our control beaker, which means I'm testing it to see what happens without any kind of washing procedure. So I'll put in the drops of the indicator and we'll see blue residue. Sometimes it's on the sides, sometimes it's on the bottom, but that blue residue is a positive result. It means there's iron in the beaker. Then in beaker 2, what we're going to do here is we're going to rinse it one time with 10 milliliters of deionized water. That's going to so the process for rinsing means you're going to measure 10 milliliters from a graduated cylinder in your drawer. Make sure that one's clean. So 10 milliliters of water with the cylinder, pour it into beaker 2, swirl it around, and then we're going to dump it into beaker 1 as waste. So our control beaker becomes our waste beaker. Once we have dumped out that rinsing solution, we will add our indicator. It's probably still going to turn blue because most of the time one rinse is not enough. Sometimes it is, and if it is for you, that's okay. You and your partner would stop the rinsing part of the experiment at that point. But most people are probably going to need to do a 2-rinse test in beaker 3. So the process is fill your graduated cylinder, the little one, to 10 milliliters of DI water, dump it into beaker 3, swirl it around, rinse it out by dumping into beaker 1, and then repeat that one more time. So you've done 2 completely separate rinses in beaker 3. The results vary on this one. Some people get positive, some people get negative. Let's pretend for our example here that we get a positive test, so it turns blue again. Then in that case, we will go ahead and go to beaker 4. And in beaker 4, we're going to go ahead and do 3 separate rinses of 10 milliliters each. Okay. Let's pretend like that does not turn blue. What you're going to see is the indicator solution we're using is a yellow color. That's not particularly yellow, but hold on, I'll do better. So the indicator starts out as a yellow color. Here we go. And so if we see yellow in the beaker, that's a negative result. What we're looking for positive results is going to be blue. So let's pretend like in my experiment, this is an example, yours will be different. I rinsed 3 different times with 10 milliliters each time, and I got a negative result. Then I don't need to do anything with beakers 5 and 6. But in beaker 7, I'm going to do 1 big rinse because of that same volume. So if yours was negative in beaker 3 with 2 rinses, then you do 20 milliliters. If it took 4 rinses, it'd be 40 milliliters. So it's based on your experiment. But by doing this, we are going to be able to have 2 different hypotheses on the trace contamination experiment. We're going to have one of them about the number of rinses, in this case, 10 milliliters each, to get something clean. And we're going to have a second hypothesis about whether a large rinse of the same volume is better or multiple small rinses is better. Okay, so 2 different hypotheses about trace contamination, about how we clean our glassware. If you and your partner are doing this experiment and you get to beaker 6 and you still don't have, well, say beaker 5 and you still don't have a negative result, you should raise your hand and have me come look at your stuff and explain to me how you've done things, and we can talk about it. We don't have any extra beakers. So if you're at beaker 5 and you haven't seen a negative result, come and chat with me and let's figure it out. Okay. That's part A of the experiment. It allows us to test a hypothesis about the graduated cylinder's uncertainty, about transfer loss every time we move material from one container to another, about how many times we have to clean something, how many times we have to rinse something for it to really be clean, and then whether 1 big rinse or many small rinses is more effective. So that's 4 hypotheses in part A. Okay. You're going to want to develop your own phrasing and your own tests. Nobody's hypotheses should be identical. So think about how you can phrase those things in a way that makes sense for you. But that would wrap up part A of this experiment. When you're completely done, you will have two sources of waste. One of them is beaker 8, which is reusable. So we're going to put that in the orange stuff or brown stuff jug. The other waste is beaker 1, which is full of blue waste and soap and all kinds of stuff. That needs to go into the container that's marked blue stuff on the side bench. That is not recyclable. That is hazardous waste that we dispose of. Be extremely careful not to put anything with the indicator in it, so anything from beakers 1 through 7, into the recycling material. So if the jug in the waste container looks orange or brown, don't add anything blue to it. Okay? So that's part A. We're going to use all of our regular PPE for this because it is a little bit hazardous. But it's really important to do this part of the experiment and refer back to it in our future experiments because it is all about error, uncertainty, parallax, contamination, all kinds of errors that we can prevent in the future or that we can't prevent, like uncertainty. Are doing part B of the trace contamination and exploring matter experiment. So our goal here is to take a whole bunch of physical characteristics of a mixture and identify what we get after we have done some heating and filtration and crystallization, okay? So the mixture you're going to work with has 5 things in it, and it's a very, very thick, pasty material. So you're going to want to always make observations, very detailed, like we did in week 1, of the materials at every single step of the process. This is going to help you identify what is in each part of the mixture and each part of the separation. So initially, we're starting with table salt, sand, charcoal, benzoic acid, and glycerol. Okay, so these are all mixed together in one jar. And you're going to use a plastic or metal spatula. Don't use glass. It's too thick and the glass will break. But we're going to use a plastic or metal spatula to scoop out the material that we're testing. Okay, so you're going to want to read through the procedures and look for some details that are pretty important, like how much of the material do I need to put in, and we're going to use the same scales as last week to measure the amount of starting mixture. These physical properties listed in the procedure, in the experiment rather, on page 29 are a key component in figuring out what's going on. So to explain them, appearance at room temperature, so 20 degrees Celsius is room temperature, will give us an indication of what state of matter we would see if this was isolated by itself. So if I, think about table salt, that looks like a white crystal, a powder almost. Sand is beige and it's also a crystal. Charcoal is a black powdered solid. It's not a crystal, so it doesn't have a regular repeating shape like the other two do, but it's a solid. Benzoic acid by itself at room temperature is also a solid, but it has crystals. Glycerol is a clear, colorless liquid at room temperature. Okay, so then we have solubility in cold water. So if I have ice water, salt will still dissolve. That's what solubility means. It can dissolve. So salt is soluble in cold water. Sand is not soluble in cold water, so it will be a solid kind of that sinks to the bottom eventually of a sample of water. Charcoal is the same thing. It does not dissolve. Benzoic acid also does not dissolve in cold water. And then glycerol does. So that clear liquid that is glycerol will mix completely with water, which is also a clear liquid. So we could not tell visually if we had glycerol with water or not. And then we look at the hot water solubility. The only one that really changes is benzoic acid. So if you have boiled your water, the benzoic acid will dissolve in it, where if it's cold water, it will not. Then we have melting points. So we're going to have the opportunity to measure melting points. And so, for example, if we had made table salt, it would melt at 801 degrees Celsius. We're not going to be measuring boiling points in this experiment because, as you see, they're quite high. But if I could boil table salt, I would need like a furnace to do that or a volcano. Then it would be around 2,700 Celsius. Okay, so that's really hot. Um, we're not going to boil sand or salt or anything, so don't worry about that. But we are going to do a melting point of our final crystals once they're dry. And that'll help us to identify which of these materials we have isolated. So we're going to want to refer back to this table on page 29 when we're doing our lab report because it will help us support and use the evidence from the experiment that we're going to collect to figure out what material we isolate. So to get started on your isolation, again, read the procedure so you can answer the pre-lab questions here. But we're going to set up this to get started in our experiment. So you're going to learn how to use a Bunsen burner this week. I'll show you that in lab, but there's videos linked in the digital copy of the lab manual. If you would like to go look, you can pull that up on Brightspace. I did demonstrate it in lab in week 1 as well. So, but you'll get to practice this on your own. What we're going to do is measure out the amount of our mixture and then add some water to that. Anything soluble in cold water would dissolve right away. But we're going to also heat up this water until it's boiling. You're going to want to use your stirring rod, the plastic or the metal one, to mix this occasionally. We have, what's hard to see on here is there is a wire screen right there that is keeping the beaker up. And then we have a circle here called a ring stand. So your ring stand and then wire screen and then beaker all go above the Bunsen burner. I'll have a setup in the lab for you to look at so you can see it in 3 dimensions. And then down here we have another ring stand right here and then a funnel. So the funnel's in your drawer. The beakers are in your drawer. Although you'll have one extra on the chemical tray because you only have one 250 milliliter beaker, but we'll want to make sure everything is clean before we use it and then set this all up and get it ready to go. I will show you how to fold the filter paper that fits into this funnel, okay? But when you come to lab, you can look at the setup. We'll talk about the filter paper, and then you can get started on this part of the experiment at any point during the lab day. So we're going to boil our hot water mixture for a while, and then we need to use beaker tongs. So beaker tongs are located on the side of the room, on both sides of the room. They are not in your drawer. Don't put them in your drawer because other people need to use them, okay? And so beaker tongs are one way of handling hot 250 milliliter beakers. We would not use them for beakers that are smaller or larger than that. It's specific to these sized beakers. They fit perfectly right in there. But they have rubber on them, which makes it ideal for gripping. So you get these sort of rubber curved pinchers, and then the handles come out the other way. So they kind of look something like that. I'll show them to you in lab. You can grab beaker tongs whenever you need them during lab. So they're always in the drawers to use at any point. Remember, though, that hot glassware and cold glassware look exactly the same. So for today in lab, you need to make sure that you're treating everything like it's hot. Okay, so don't just grab onto something. So we'll use beaker tongs to hold the boiling water and unknown mixture. And then what we'll do is pour it into the filter paper. You want to try to pour it right into the center of the filter, right into the middle, so that you're not losing your solid underneath the filter paper. So if we go right into the middle of the filter paper, it will capture all of the materials that are solid. All the things that are insoluble in hot water will get trapped in the filter. Okay, so when we do that, the liquid that comes through the filter paper is called the filtrate. Okay, so the filtrate will be in the beaker here because it makes it through the filter. The precipitate is what gets stuck. That was everything that was insoluble. All right, so the precipitate gets stuck. I can't really adjust where that is, but you can see it'll be stuck in the filter paper. When you're done and filtering, once it goes all the way through the filter, you're going to let the filter paper cool off, but you're going to put your, I just realized you need to have two pieces of filter paper in there when you do your hot filtration. So make sure you and your partner each get a chance to fold a piece of filter paper along with me, and then you're both going to put your paper into the funnel for this part of the filtration. That's just to make sure we capture everything. Okay. So anyway, you're going to let the filter paper and the filtrate separate from each other. And then you're going to take the beaker that now contains your filtrate and put it back onto the Bunsen burner to boil again. Meanwhile, once the precipitate and filter paper have cooled off, you're going to take that filter paper out, spread it out gently. It's going to be wet, so be careful not to rip too much. But spread it out and look at the precipitate. You got to make observations of what it looks like. So again, we're going to use all the adjectives just like we practiced in week 1. Okay. Once the filtrate has boiled again, you're going to remove it with beaker tongs and let it cool. Once it is cool enough for you to touch, you're going to make an ice bath. An ice bath just means you take a beaker larger than this one and you put a little bit of ice in it, maybe halfway full, and then a little bit of water, about, halfway full. And then you're going to snuggle your filtrate down into that ice. It's going to take some time, but eventually you'll see crystallization happen. That means little pure crystals of a precipitate, so something that's insoluble in the cold water, will form. Eventually, you will be able to filter that and collect just the solid by itself. We're going to either let that dry in our drawer, or we might have time to put it into our oven and dry it in the oven and do the melting point in week 2. If we have to leave it in the drawer to dry, we'll do it at the beginning of week 3. Okay. But that's your part B, exploring matter portion. We're exploring how to use physical changes to separate different chemicals from each other and how to use physical properties to figure out what we have separated. As you might expect, the hazards of that part are going to be hot glassware, boiling water. We want to make sure to use the beaker tongs. We also have hot mitts over by the oven that you can use if that's easier for you. But we definitely don't want to grab onto hot glassware with bare hands, of course. We're also going to use PPE for that whole experiment. Some of those things are irritants, so we don't want to get them on our skin or our eyes. The waste for that part of the experiment, the solid parts can go in the garbage can with your filter paper. Please don't leave those in the sink. Put them in the trash. And then you're going to keep the little white crystals to do a melting point on. Or if you finished with the melting point, you're going to put that on the tray on the side bench where Kate leaves a beaker for the white crystals. And then the liquid part of the filtrations is going to go in the sink. Okay, there's nothing hazardous once we have done that final liquid filtration at the very end. Okay, so the hypothesis for part B could look like something where you pick one of the 5 components of the mixture and say that at the end, the melting point will be whatever the melting point is for that component, because that's what you think you're going to isolate. So if I thought charcoal was the thing I'm going to end up with at the very end of the experiment, then I would say it is hypothesized that charcoal will be isolated. This will be confirmed by measuring a melting point of 349 degrees Celsius. Okay. Um, you'll want to write your own hypothesis. You can read through the procedure and come in with any questions you might have. You're going to do both parts with partners because I realize you need two 250 ml beakers, but it's important that both people learn how to um, start the Bunsen burner and control the fire and move hot glassware around. So try to share those duties as you're working. Okay. So complete this quiz. You can take it as many times as you want to be successful. And then I'll see you in lab. Don't forget that this pre-lab quiz has to be done before you come.